The SARC DTI Transputer Initiative's purpose was to promote the use of transputers in a variety of applications. In this context, 2 control instrumentation demonstrators were commissioned to illustrate this point. Hector is the robotics demonstrator. This robot demonstrates the application of transputers handling a real-time control task, illustrating graphically the parallel and concurrent nature of the processing required. The form of the demonstrator lends itself to a modular design which is both easy to transport and then assemble for exhibition. However, this modularity has a specific purpose apart from simple convenience. The modularity maps both physically and logically onto the behavioral control model that underlies the actions of this robot. Hector is composed of 3 processor segments, each consisting of a T425 transputer mounted on a size 1 tram and supporting microcontroller driving the servos. Each segment is identical and essentially autonomous, having the same processing capability and running an identical copy of the behavioral model. The use of a behavioral model to describe the complexity of action required is not new. Similar work has been performed at MIT with a robot called Genghis. Within this model, the various layers of behavior are arranged hierarchically, such that the lower level behaviors are subsumed within the higher levels. For the case of walking behavior, this means that the basic behavior determining the stance is overridden by that producing the gait. However, the stance still calculates compensating leg angles to maintain the same mean stance. Therefore, the effect of the walking behavior is to override one or more legs whilst the remainder compensate, giving rise to locomotion. The alternating tripod is the most simple and basic gait, both in terms of calculation and mechanics. With the same robot, we can also demonstrate a ripple gait. That is one where only one leg is advancing, whilst the remainder compensate to give this form of locomotion. This walking behavior shows that the continuous recalculation of the underlying stance is distributed across the segments of the robot, given the correct relative positions of the legs, such that the correct phase relationship is maintained throughout a gait cycle. From a mechanical point of view, the ripple gait offers the advantage over the tripod gait of being more robust, having 5 legs in contact with terra firma as opposed to 3. However, this is not without cost. Due to the leg slew rate limitations, this gait must be intrinsically slower. This improved mechanical robustness can be demonstrated by the way in which the ripple gait can cope with a low obstacle. As the behavioral model for this gait both takes deeper steps in its stride and detects leg contact when advancing forward, Hector can both raise his legs sufficiently to step upon and lower them sufficiently to step down when over. Hence, this extra behavior allows this type of robot to negotiate uneven terrain like this. This would be difficult to do with the tripod gait, as the extra effort of the additional legs is required to help push Hector up and over. Although slow, the ripple gait could be described as being cautious. Whereas coping with uneven terrain requires the subsumption of the leg lift component of the walking behavior, collision avoidance must subsume the leg advance component. When Hector's feelers make contact with any obstruction, the leg advanced angle is reversed. As before, the remainder of the legs calculate the compensation required and reverse locomotion is achieved. Obviously, this sudden change of direction and relative phase requires that at least one step of walking on the spot has to be performed before correct movement occurs. At the highest levels of the hierarchy of behaviors is the tracking behavior. Hector may be either equipped with an infrared sensing head, which is a little short-sighted, or a voice-activated head, which is not shown here. In either case, given appropriate stimuli, Hector turns towards the source of the infrared emission, or in the case of the voice-activated input, in the direction specified by the command. There is some delay with this, as again, the new leg behavior has to be given time to take effect. It can be seen from these demonstrations that a reliable form of locomotion can be achieved using a behavioral model. Indeed, as said before, similar work has demonstrated as much. However, there are a number of significant differences here with Hector. Hector demonstrates that given appropriate symmetry of behavior, here to be found between leg pairs, this model may be replicated in a number of identical segments to achieve the overall desired behavior. To achieve this, enhancements have been incorporated into the basic behavioral model, allowing data to be distributed between body processing segments. In processing terms, this is all grist to the mill for the transputer.